Welcome to question 9 of the 2019 Mathematical Methods Exam 1 for the Southern Hemisphere. In this video we will be looking at the solution and examination advice for this question. A reminder that this video is in no way endorsed by VCAR. For question 9 we want to consider the functions f and g, where f is this function with a rule 3 plus 2x minus x squared, and the function g has the rule e to the power of x. And you can see that both of them have a domain that's all real numbers. For part A, we want to state the rule for g of f of x. So g of f of x is just found by taking g and subbing f of x into it. So this is going to equal, and the function e is e to the power of something. So we have e to the power of, and then we just put 3 plus 2x minus x squared into the power position. Wherever there used to be an x, we put f of x there. So this is going to be the answer to part A of this question. For part B, we're asked to find the values of x for which the derivative of g of f of x is negative. So if we want to find the values of x where the derivative is negative, the first thing we need to actually do is calculate the derivative. So that means that we're going to calculate the derivative, which I'm going to write as d dx of the function we just wrote above, which is e to the power of 3 plus 2x minus x squared. And that derivative is going to be found using the chain rule. And that's because we can spot a function inside a function. So just over here, I'm going to let u be equal to the inner function. So that's the 3 plus 2x minus x squared, or in other words, that's f of x. And that means that y is just equal to e to the power of u, which was the g of x function, or the outer function. So du dx is going to equal 2 minus 2x, so that's just the derivative of that quadratic. And dy du is just going to be e to the power of u, because we know that e to the power of u differentiates to itself. So to finish the chain rule off, we just take dy du and multiply it by du dx. So that means we're going to have 2 subtract 2x multiplied by e to the power of 3 plus 2x minus x squared. So that's the derivative function. And to find when that's negative, we're going to solve that to be less than 0. So therefore, we actually can consider 2 minus 2x to be less than 0. So that's the main thing that we need to look at, as e to the power of 3 plus 2x minus x squared is greater than 0 for all values of x. So it must be that linear 2 minus 2x that's less than 0, which gives the derivative being negative. So therefore, we can see that 2 must be less than 2x. So that's just found by adding 2x to both sides of that inequality. So therefore, once we divide by 2, we find that x must be greater than 1. And you might actually just find it more convenient to write it like that. So x being greater than 1 is the answer for part B of this question. From the examiner's report, we can see that 94% of students got part A correct, which was just finding a rule for g of f of x. And that the examiner says that this question was well done for the exam. 9b has a big drop off, with only 22% of students getting full marks for that question, and almost 60% of students getting no marks. And then the examiners go on to say that generally students applied the chain rule to find the derivative. However, a poor expression resulted in incorrect answers for many students. The expression 2 subtract 2x times e to the power of 3 plus 2x minus x squared is not equivalent to the one shown there without the brackets. So it just goes to show how important the brackets are when we are finding derivatives and then subsequently working with them. And then it goes on to say that some students did find the correct answer, however it was not supported by correct reasoning, which is really what's required in a 2-mark question. For part C, we now want to state the rule of f of g of x, where we're considering the same two functions. So f with g of x substituted in is going to equal, and we start with our outer function f, which is 3 plus 2x, but wherever there's an x, we're replacing it with e to the power of x. And then we still have a minus x squared there, which is going to be minus e to the power of x squared. And now we can simplify that slightly to just be 3 plus 2e to the power of x minus, and then e to the power of x to the power of 2 can just be written as e to the power of 2x. So that would be the rule or expression for f of g of x. And because it asks for the rule, it's best to have f of g of x at the start of the answer. For part D, we're then going to solve f of g of x, which we just found above, equal to 0. So let's go and write that down. So what we're solving is 3 plus 2e to the power of x minus e to the power of 2x is equal to 0. And this will actually result in finding a hidden quadratic inside that equation that we're trying to solve. So the first thing I'm going to actually do is I'm going to rewrite this with a positive e to the power of 2x. So to do that, we can just multiply both sides of the equation by -1. And this would give us e to the power of 2x minus 2e to the power of x, subtract 3, is equal to 0. So those two equations are equivalent, and I've just multiplied the top equation by -1 to get that second line of working. Next, just to make things easier, I'm going to let a, capital A, equal e to the power of x. So therefore, when we have e to the power of 2x, that's just the same as a squared, minus 2 lots of e to the power of x, which is just subtract 2a, minus 3 equals 0. And now we can see where that quadratic has come from, which I described earlier. Next, we just want to factorize that expression. So we look for the factors of -3 that add up to -2. So in brackets, I can have this as a subtract 3, bracket a plus 1, and that's going to equal 0. So that factorized form is equivalent to the quadratic up above. And then using the null factor law, we find that a could equal 3, or a could equal -1. However, we know that a is simply e to the power of x, so what we're actually solving is e to the power of x could equal 3, or we could have e to the power of x equals -1. If we have a look at those two options, e to the power of x equals -1 will have no solution. And that's because when you try and take an equivalent log expression, you'd have log e of -1, which doesn't exist. And another way of thinking about that is that the graph of e to the power of x has an asymptote at y equals 0, so it never goes below the x-axis, which means it never equals -1. However, for our other option, e to the power of x equals 3, that does give an answer of x equals, and we'd have log e of 3 for that equivalent log expression. So that is the solution to this equation, and therefore the answer to part D of this question. From the examiner's report, we can see that 86% of students got part C correct, and that overall that question was well done. Some students did incorrectly state f of g of x with an e to the power of x squared rather than e to the power of x squared in brackets. So that's important that you get that right, because if you have e to the power of and then x squared in the power, that's a different expression. So when simplified on the previous page, we saw that this is equal to 3 plus 2e to the power of x minus e to the 2x, not e to the power of x squared. So just be careful with placement of brackets and applying index laws. For part D, just under 50% of students got this question correct, and the examiner's report goes on to say that most students were able to form a quadratic equation to solve as a part of that process. Some students did falter with the correct factorization which was required in this question. And the inclusion of x equals log e of -1 was a common incorrect answer, which we discussed wasn't a solution, or it's actually undefined, so it's not an answer to this question. For part E, we're now asked to find the coordinates of the stationary points of f of g of x. So previously we'd already found the rule for f of g of x, and that was equal to 3 plus 2e to the power of x minus e to the power of 2x. Therefore, to find the stationary points, we're going to derive that expression. So we're going to calculate the derivative of 3 plus 2e to the power of x minus e to the power of 2x, and we're going to let that equal 0. So the derivative of this, it's just 3 separate terms that we can derive individually. 3 is a constant, so its derivative is 0. then the derivative of 2e to the power of x is actually still 2e to the power of x. And then the derivative of negative e to the power of 2x will be minus 2e to the power of 2x. And that is what we're going to solve equal to 0. And like part D, we actually get a quadratic equation appearing here as we have an e to the power of x and an e to the power of 2x. This time I won't substitute a in or anything like that. I'm just going to factor out 2e to the power of x. And here you just need to be careful that factoring that out will actually leave a 1 there, and then a negative e to the power of x as the other part inside that bracket, and that's what's going to equal 0. Using our null factor law, we would say that 2e to the power of x could equal 0, or that the second factor, which is 1 minus e to the power of x, could equal 0. Our first option results in no solution, and again that's because the equivalent exponential statement would have x equals log e of 0, and we know that we can't have 0 inside a logarithm. However, for our second option, we would just add e to the power of x to both sides, and we'd find 1 equals e to the power of x, and then taking an equivalent log expression, this would give x equals log e of 1. However, log e of 1 is simply 0, so this gives x equals 0 as the solution to that equation. However, just to reiterate, we did need to find the coordinates of the point, so we now need to substitute this back in to f of g of x. So substituting x equals 0 in means we'd be trying to evaluate f of g of 0, which is going to equal 3 plus 2e to the power of 0 minus e to the power of 2 times 0. And then e to the power of 0 is 1, and e to the power of 2 times 0 is still e to the power of 0, which is equal to 1. So this is going to equal 3 plus 2 times 1 is 2, minus 1, which equals 5 subtract 1 is 4. So the coordinate is going to be x is 0, y is 4. So that is the answer to part E of this question. From the examiner's report, we can see that 30% of students got that answer fully correct, with 28% of students getting 1 mark and 42% of students getting no marks for that question. The examiner's report goes on to say that this question was well attempted, but not done very well. Common errors included an incorrect derivative and leaving off the y coordinate from the stationary point. So a reminder that the answer was 0, 4 and not just x equals 0. So for part F, we want to state the number of solutions to the equation g of f of x plus f of g of x equals 0. And you may be wondering why you did all that work in parts A to E. And I've included our responses and our answers here so that we can use them to help answer this question. So before we go too far into this, I'm actually going to rewrite this equation as being g of f of x is equal to negative f of g of x. And that means the number of solutions is really just related to the number of points of intersection between those two graphs. So my approach for this question is going to be graphical. And now I've just included a ruled set of axes here to keep it neat, but you could obviously have done this on the exam paper as well. So the first graph I'm going to try and sketch, and I'll be as accurate as I can without wasting too much time, is g of f of x, which I'll do in blue. And its rule, we know from before, was e to the power of 3 plus 2x minus x squared. And that was found in part A, and part B told us when its derivative was negative, so when the graph slopes down, and when x is less than 1, it'll actually be sloping up, if that makes some sense. So in other words, when x is equal to 1, we get a stationary point on the graph. So if I just put 1 here, we would have a stationary point here, and on the left-hand side, so when x is less than 1, we'd have positive slopes. So it's actually going to look something like this. And when x is greater than 1, we have negative slopes. So it would look something like this. So that's a sketch of g of f of x equals e to the power of 3 plus 2x minus x squared. And now you may be wondering why we know that that is the shape of the graph. And what I'm going to get you to do is just consider that power. So if we had a little sketch of that, that's going to be a quadratic that's upside down. That's the most important thing about that. and it would look something like this. And the important thing here to know is that as x gets closer to negative infinity, the quadratic's value gets closer to negative infinity. And e to the power of negative infinity is going to get really close to 0. And the same as x gets towards positive infinity for the quadratic, the y value still gets towards negative infinity, and e to the power of negative infinity is going to be close to 0. So we will end up with an asymptote as well for this graph. So if I just dot that on as well, it would have a rule y equals 0. And now just to put a bit of detail on this graph, that would have an x value of 1 and a y value, once I sub 1 into here, it would just be e to the power of 4, which is quite a large number. And not that you need to, and it would waste a little bit of time in the exam, but this point here when x is 0, you could find that the y value is e cubed. So that's another reason why we know that it's less than the turning point at the top there. So now that we've sketched that graph, the next graph we need to consider is negative f of g of x, which I will do in red. And we already knew from part C what its rule was, and now we just multiply that by negative 1. So we're going to have e to the power of 2x minus 2e to the power of x minus 3. And this minus 3 constant at the end is actually going to be really important for the way this graph behaves, because that's going to end up being an asymptote to this graph. So I'm going to sketch that on first, and that rule is y equals minus 3. Now the next things we know about this graph is it is going to have an x-intercept at log e of 3. So that was what we found in part D. And log e of 3 is just a little bit bigger than 1. So log e of e, which is about 2.7, would be 1. So log e of 3 on the x-axis is just a little bit bigger than 1. So there's going to be an x-intercept there. And then we also know that there's a stationary point at 0, 4. However, that was on the graph of f of g of x. We're graphing negative f of g of x. So after a reflection over the x-axis, this coordinate's going to be 0, negative 4. So that's going to be just below here. So with an asymptote, with a turning point, because that is a stationary point, it must turn there, and with an x-intercept of something that's just a little bit bigger than 1, the shape of this graph is actually going to look something like this. So it's going to turn here, head back up, and then it's going to keep getting bigger and bigger and bigger past that point. And we can see now that there is exactly one point of intersection where those graphs cross. So we're not particularly interested in what the coordinates of that point are, just the fact that there's only one point of intersection, so there's one solution to that equation. So that is the answer to part F of this question. And just before I move on, if you wanted to label these points, that would be 0, negative 4, and that point there, which is the x-intercept, would have been log e of 3, 0. So again, the graph's not essential, but it helped us find the fact that there's one solution to that equation. From the examiner's report, we can see that they identified that there's only one solution, and that the question was not well done at all, with only 19% of students getting the answer to that problem. And I suspect that many would have just guessed that it was either 0, 1, or perhaps 2 solutions. The examiner goes on to say that very few students attempted to draw a rough sketch of each equation and use addition of ordinates or something similar. We didn't use addition of ordinates, we actually used the points of intersection between one of the graphs and a reflected version of the other graph. But again, a sketch or something like that was really key to answering this particular question.